Hey there, folks. I'm a little casual today. I hope you apologize. It's Sunday afternoon. I do have on a math shirt, so it's take it to the limit as x approaches infinity. One more time. So one of our old math shirts. So anyway, we've got just the one problem left in 5.1. So let's take a look at it. And it was problem 17, which had actually 4 parts. And they were all true. They said, okay, give a proof by counterexample, or give a proof or give a counterexample to each. They're all true. So let's prove them real quick. Okay, the first, and I could do. If it would, this could be a little bit larger. Hold on just a second. Just notice that it's not as big as it could be. That does the auto business. Okay, that'll have to do, I guess. Okay, so if R is reflexive, then we want to show that R inverse is reflexive, and that's actually pretty easy. Let's prove that. Since R is reflexive, what does that mean? Well, it means that that's a little better, I guess. Since R is reflexive, that means then that AA is an element of R for all A in the set A. It's relation R on A. Then, well, the inverse relation would have the flip of that, which is just AA. For all A in A. And that's it. Thus, our inverse is reflexive. Okay? So it's not too hard to show. It's still not the best. Not the best quality. I don't know if I can do anything about that. Let me try it real quick. Oh, there we go. I don't know what I did, but that's better. Okay, great. All right. So let's prove the second one. It says if R is transitive, then R inverse is transitive. Now the way you prove that is you say, well, suppose you have A related to, in this case, R inverse, A related R inverse to B, and B related R inverse to C, or you could say you have both those ordered pairs, and then say prove that there's a shortcut between A and C. All right. So we'll say that. Proof. Suppose that there exists A, B, C, and A, such that AB and BC are in R inverse. Okay? And what we're going to show is that AC would be in R inverse. Okay? Well, since these are in the inverse, the flip-flop of these would be in R. So we got BA and CB in R. But if C goes to B and B goes to A, then C must go to A because R is transitive. Since R is transitive, then CA is in R. And that means that AC is in R inverse. Thus, R inverse is transitive. Right? That's what we're trying to show. Okay, these aren't too bad. All right, see, if R is symmetric, then R inverse is symmetric. Well, what we have to show is that if we have A and B, A comma B in R inverse, then we've got B comma A in R inverse, right? So we'll start with that. Suppose we've got AB in A such that the ordered pair AB is in R inverse. Then that means we've got BA in R. And then since R is symmetric, we've got AB, right? Is in R. And then that means we got BA in R inverse. Because that's what inverse is. You just flip-flop the first and second coordinates. And that's enough, right? We had to show for every AB that I've got BA, which I did. Thus, R inverse is symmetric. Okay? And then finally, if R is antisymmetric, then R inverse is antisymmetric. Okay, now the way we show this is we say, all right, suppose we've got both A related by R inverse to B, and B is related R inverse to A. Show that A and B have to be the same element. Okay? All right, so let's prove that. Suppose there exists, I suppose I said that there too. Suppose there exists A, B, and A such that AB is in R inverse and BA is in R inverse. Okay? And now we need to show that they're equal. Well, then take them back over to R, right? That means that BA is in R and AB. Swap the ends, right? It's an R. Well, since R is antisymmetric, that means A and B are equal, right? And that's all we had to show, right, for R inverse. Thus, R inverse is anti-symmetric. And that's it. I didn't put my little blocks, little boxes. Okay, and that was the last problem in 5.1. We will pick up in 5.2. All right, see you in just a few minutes.